So GC instrumentation and a common detector, the FID. So Brandy, what's our mobile phase in gas chromatography? A gas, yeah. And which gas is it upstairs? Anybody know? Hydrogen. Is hydrogen explosive? It's 99.99% pure. On its own, no.
Hydrogen bombs.
Needs to mix with what?
It has to be in a high concentration, right? Mixed with oxygen.
Oxygen. It needs to, you're right. It needs to be at the right concentration. You need to reach a certain explosive level, but there has to be oxygen there. So I've read several sources on this because, you know, you just take a little balloon of it and the stuff is just, it's a huge explosion. That's because it mixes with oxygen in the air. But what if there was a leak upstairs? You have that thousands of pounds of pressure of hydrogen. That's a lot of hydrogen upstairs, right? And there's a little leak. Bless you. And from what I've read, that it's impossible to reach an explosive limit with hydrogen because the stuff just escapes. You have to have a room that's completely sealed. And then the gas that leaks out, because hydrogen is still light, it just leaves. So, I mean, I don't know, I wouldn't want to trust that idea, but that's what I read. What I still to this day don't understand though, and maybe this is another thing, I just haven't found it on the internet or anywhere. There's a fire. You've got a huge tank, yeah, it's cast iron, and I know it's really thick and things, but it's a big tank of explosive gas, and there's a fire in here. I mean, you're a fireman, you should be aware of that, right? Shouldn't there be signs outside the door? The fire department knows. I mean, I just don't, it must not be able to, it must be safe. I don't know, right? Because why wouldn't there be something on that? But anyway, I've always been curious about that. If anyone figures that out, let me know, and I'll give you some bonus quiz points, right? Why isn't that a big deal? Almost all gas chromatography performed today utilizes capillary columns. So Andy, at the head of the column, when doing GC, the sample is vaporized would be the best word. I agree with that. Okay. So they're using some techno speak here in this next one. They're saying that here's your capillary column, right? And here's your glass, right? And it's capillary, so it's got this big open hole in the middle, right? But inside is coated with this stuff, right? All the way around is coated. Proprietary, patented, secret, big whoopee how they got it there, okay? And it needs to be really uniform, and they're going to coat it with different compounds, okay? If we're doing reverse phase chromatography with a gas chromatograph, that inner layer is probably what type of material? Very organic, just like HPLC. So, but it's a liquid. It's not a solid, it's a liquid. So really, we're not supposed to say GC. We're supposed to say, I guess technically, GLC, because everybody does gas-liquid chromatography. Your compounds that you're eluting, what you inject are, you know, they're like dissolves like, they're partitioning, they're dissolving into that liquid phase, right? And the more organic it is, the more like it is the liquid phase, the more it will be retained, right? It'll have a higher affinity, okay, for that stationary phase. Are these capillary columns pretty long? Alyssa, how long are they, pretty much? We haven't got to this, but I don't remember if you've seen, I don't think any one of you had seen the inside of our GC. I just pop open the little drawer, and it's, geez, it's a coil that's probably like a foot wide, and it's just wrap. It's like 30 meters long. It's really long. our GC instrumentation flow diagram. So Mel, what the heck is this Mickey Mouse looking thing?
The valve, pressure valve?
Yeah, we called it the gas, starts with an R, regulator, right? So remember, one of these gauges read the pressure that's inside the cylinder. The other one read the pressure going outside the cylinder, right? So this pressure regulator has to be connected to our GC. So that pressure regulator has to be connected to our gas, our mobile phase. Like you said, our mobile phase is hydrogen gas. Okay. Do you recognize, Andrew, this green square? Purposely made it green. Yeah, that's the. Now maybe you haven't changed the septum yet, but that's the little green nut. You follow the logbook, and if you're the third user, you're supposed to unscrew the green nut and pop out the little rubber septum and put in the new one because they get worn out. So that's the green nut. Okay. So that's essentially our injector, our inlet, right? So you inject, right? It vaporizes, goes into our column, which is really long, upwards of 30 meters or longer. Whoop. Oh, erase the whole thing. And then ends up in our detector, any detector. We're going to talk about FID, but there's our detector. So this is our inlet, our detector. So our detector better be hooked up to our computer, right? Brandy, what do you think this dashed line is doing around this whole thing? The little green nut is outside of the dashed line, but everything else is inside it. Anybody know? An oven. Why is it an oven? And there's a huge fan in the back. I'm not going to draw the fan, but so they can remove that, can change the temperature really quick, and it can really control the temperature really well. Why an oven? If you want to do liquid chromatography, what did you change easily to do chromatography? Did you move peaks around to try to resolve them, try to make separations? What do you change that's really easy to do on that instrument? You can change several things, but one of them is what you're supposed to really be focusing on. Yeah, flow rate is on the LC. Temperature, flow rate, it's not going to have a dramatic effect like this other, what you haven't mentioned yet. You change the what composition? Mobile phase. You change the mobile phase composition. That moves peaks all over the place. So that's what you do in LC. What do you do in GLC? Temperature. That's why this dashed line is all around there, huge insulated walls with a big fan in the back so you can change the temperature on demand. 5 degrees per minute. Let it cool down, let it heat up, whatever you want to do there. Usually heating up is a lot easier, more controlled. So that's all an oven. Okay. So we're going to, before this period is up, we're going to zoom in on the inlet, talk about its parts, and we're going to pick a detector, the FID, and see how it works, and take a look at its parts. Here's, if you swing open that door on our GC, this is what it looks like. So, Alyssa, do you recognize anything? Yeah, where would you say that is? Yeah, I agree with that. See how it's kind of insulated too? Here's our inlet. Andy, you recognize anything else? Yeah, this here, there's our column. All right, coming out of our inlet, going up into our detector. Andrew, recognize anything else?
The fan in the back.
Yeah, that big fan. Look at that big fan. It's a big fan blowing around. I can't draw a fan, but right? Anything else, Brandy? Pretty much recognized everything, I guess, but
The oven.
I guess the oven, right? You got these big, thick, insulated walls, right? These are really thick and insulated walls. Okay, so I guess you could talk about that. Right? It's really thick, insulated walls. Okay. Our FID. Looks like an FID stands for, Mel? Flame ionization detector. Good thing she bought her manual. Okay, here it is. I can pass it around. Notice how this is how it's oriented. And there's a little electrical connection, and all that's connected to is just this metal big thing on the outside. Okay? And you can tear it apart and...
That's the detector?
Yeah, this is the FID detector. And kind of see what's going on. Oh, man, look at all that carbon. It's really dirty in there. All right? So you can play around with that. But how does it work? Flame ionization detector. Well, the name kind of gives it away. There's a flame in there. So it must be doing what to everything that's coming out of the column? What's that? Must be doing what? Everything that enters from that column, right? If the column's supposed to be doing its job, everything that's coming out of that column are these pure components, right? The least organic first, if you're doing reverse phase chromatography. But you have these pure components coming out. Everything enters into that flame, and it's a hydrogen flame. That means it's really hot. What's going to happen to everything that enters it? Burn up. Because what are we injecting onto this thing? What sorts of compounds are we really interested in doing? Organics. We're doing reverse phase chromatography. Everything we're talking about has to do with organic compounds. That's all we're analyzing. That's all we're really interested in. We're not interested in iron or copper. No, that's a whole other instrument. Okay, we're interested in these organic compounds. So it's going to burn up. And what they found is that if you burn stuff, what do you always get? Or supposed to get? Do you remember, Andy, what are you supposed to get when you burn something? Water and carbon dioxide. Okay. If you crank up the temperature to that of a hydrogen flame, things burn even hotter. So energetically that you ionize the carbon ions. Any carbon that's there in this compound, it burns up. Burning is a really complicated process. So I bet you it probably does go through a stage of carbon dioxide. I'm not really sure, but it's a really complicated process. The point is the end product is carbon ions. Carbon ions. So what they do is they just have that big hunk of metal that the wire is coming out. Right, there's this big that wire that you see. They just make this really, really negative. So those carbon ions, every time one's generated, it'll just strike the side. And that's why it's so dirty in there. And it'll generate a little bit of current. So it detects it. So an FID is really a what counter? Carbon counter. An FID is really a carbon counter. The more carbons you have, the bigger the signal.
So it works like a flame.
Yeah, the flame burns everything up at a really high temperature, generating what ions?
Carbon
carbon ions. And then the carbon ions, right, generate a signal in the FID, an electrical signal, each little carbon ion. So Brandy, is it even possible for there to be something the FID cannot detect? Yeah, I guess here's what gases can an FID not detect? Is that even possible? I mean, is there such a thing? Okay, which could be what? Has to be a gas, so we can't say sodium chloride.
Well, those are negatively charged, right? Does that matter or no?
Like you said, you answered it. It's just a gas that simply does not contain carbon. Hydrogen gas. So if you're, because you remember, you just have eyes. You see this gas is being generated. You don't know what it is. So then you go put it on the instrument. You're not going to see it. That really scared this company. I think it was Kimberly-Clark. They told us this story where they had all these tanks. I was at some conference, and they were bulging. What the hell, right? So you just go sample it, this vapor that's bulging, and go put it on the instrument. Nothing, no peaks whatsoever. But yet they did their little test tube test, and pop, it's explosive, right? So they were pretty freaked out on the whole thing. And they couldn't figure it out. And then they realized, it's an FID detector. It's hydrogen gas. So, is there anything else besides hydrogen gas?
Nitrogen?
What's that? Nitrogen. It's another good one.
Water vapor?
Water vapor is huge. Because then, just imagine, and we've taken full advantage of that. You can take a look at, you pop, like I took some Advil, right? My body only digests what percent of that Advil? What percent of that ibuprofen? It metabolizes what percent? Is it a lot of it?
No.
Hardly anything. Less than 8%, easy. So, well then where's all this stuff, Advil go, that I just swallowed?
Everywhere else?
Specifically in the toilet. Well, where does all that stuff go? The sewage system, which goes to the sewage treatment plant, which goes where afterwards? At the big and well, it might end up sooner or later, right? But yeah, it kicks out the back. That's, to me, that was the most interesting tour I've ever been on with a sewage treatment plant. It was so interesting. Anyway, so what we did is, that's supposed to be a problem. You've heard of like the little froggies in Minnesota having their issues. Maybe you haven't, but they are. So the point is, because their skin is so permeable to what's in the environment. So all these compounds are supposed to be building up their environment. That was our research project. We're going to just take water samples of what's going into the sewage treatment plant, compare it to water samples going out of the sewage treatment plant. And you bet, we found ibuprofen. We found naproxen. Naproxen is a drug for people who have kind of like diabetes, high blood pressure. It's supposed to be a very common drug. Anyway, we found a lot of peaks. We didn't identify them all, but we did identify those for sure. The point is we could do this because water is invisible to this detector. It was an extremely sensitive technique. Okay. Okay. Using a C18 column, a sample of gasoline was injected onto a gas chromatograph, inlet temperature of 250 and an oven temperature of 145. Can this chromatogram be improved? If so, how? So we got to sketch something here. Here's our FID signal. Here's time. So we'll do the same thing we usually do. We have everything kind of nice and resolved down here. All right? And then way out here, At 20 minutes, we've got a lone peak, right? How could you fix this? You may not want to fix it if you're the one pushing the button and sitting around, but how could you fix it? And let's give a time for this last one. Yeah, because you're wasting a lot of time, and this 99.99959er, they call it, percent pure hydrogen, you're just wasting a lot of mole phase. What could you do?
Change the oven temperature.
Change the oven temperature to what?
Higher.
Make it higher, right? You don't know what number. That's the chromatography part. You just try it. So what could you change it to? 300. Okay, fine. 300 is a huge jump. And in fact, that's the maximum of the.
Yeah, that's what we did yesterday.
No, that was a split ratio. That
was
wasn't.
ratio, my bad.
Yeah. So let's just call it 200. So, but if you change it to 200 degrees, push go, inject it, push go, man, all this stuff you just messed up everything. So that isn't going to work. And yet the only way you can know that is if you did it, but I'm just telling you that would happen. So don't do that one. It's a little more complicated than just this. Say what? Remember, don't think about isocratic all the time.
Can you do that with 60?
Yes. That's why that big fan and that big oven are there. So you can do gradients all you want.
At the same time.
After 10 minutes. Yeah, don't mess with this. Somebody did a lot of hard work here. So after 10 minutes, just leave the 10 minutes part alone. So whatever they're doing up to 10 minutes, great, just leave it alone. After 10 minutes, crank it to 200. You can crank it to 200. Or after 10 minutes, raise the temperature 25 degrees every minute. Or, whatever. Just raise the temperature. Because that'll do what? Why does that work, Brandy? If I raise the temperature, things elute faster. Why is that? And we haven't really talked about that too much yet in GC. It's coming up. But why is this retained in the first place? We're doing reverse phase chromatography. This is the most nonpolar. This is the most organic compound. It's the most like the stationary phase. Has the highest affinity for the stationary phase. If you raise the temperature, how does that change its solubility?
Is it more soluble?
It seems like it would. But what's going to happen is if you take a liquid, right? Because remember you have this liquid phase. If you take a liquid, what's the head space? We're kind of really getting ahead, but it might help you. What's the head space? You never heard that term? Okay. If you take a liquid, where's the vapor phase? Where is the vapor phase? You just picture some liquid. Where's the vapor phase? The actual physical location. Where is the vapor phase? The liquid phase, I can point at it. Where's the vapor phase? Yeah, above it somewhere, right? On top. Okay, that's the head space. That's the head space. Okay, so how can you get more liquid into the vapor phase? Increase the temperature. That's why you increase the temperature. Okay. So you get more of everything into the vapor phase. And we'll get into that a lot heavier, maybe the next class period. But here's different capillary column types, but everybody is pretty much using this one. Okay. I think the other stuff just isn't as stable or doesn't work as well. Maybe it has its particular specific problems that it helps, but beyond that, everyone's doing GLC. I'm always amazed by this. They can bend glass, right? It's in a plastic bag, so it shouldn't break and get in your eyeballs, so don't be kind of careful with it, but
You can bend it?
you can bend it. And it's supposed to be a capillary column. So if your eyes are good enough, you could hold it up to the light and see through there, but there's no way you can see through that. But how can it bend? How can it bend? Glass, look at glass doesn't bend. We talked about this, I think we talked about it in analytical, maybe.
Yes.
Glass doesn't bend. Right? It'd be awesome if it did. These dang phones would last a heck of a lot longer, right?
The iPhone will.
Is there Gorilla Glass?
Make the glass ultra, does anyone remember this? Ultra pure. Make the glass ultra pure. No impurities. And then you can bend the heck out of it. But you can't have any oxygen around. If you have oxygen around, or if you touch it and get impurities, you can get, it'll react with the oxygen or the oils in your hand, and it's, even if you're in a vacuum and you touch it, it's going to break in that spot that the impurity or where you touched it at. So what they're going to do is take that ultra pure glass and coat it with this polymer, polyimide. And it's orange. That's why these capillary columns end up being orange. Okay? So that's how they get it to bend, is they have the ultra pure capillary columns, and then they coat it with this polymer so that it keeps, and that polymer, it serves as a coating so that you can touch it, right, and not cause a weak point. You can have it in the atmosphere and not cause a weak point because it can't react with oxygen. It's not available to it. Okay. So you okay with that? So be able to sketch. Now I don't want all the details and things. I just want the important points. What are the important points? Well, I would say the green nut. If you want to call it the green nut, or if you want to call it the septum cap, that's fine, right? You have that on top. And then you've got your little red septum in here. So that's an important part. Okay. And I'm still amazed by this, that we can put guys on the moon, but we can't come up with a material that's better than rubber for a GC. And because we want a material that's, you can puncture it as many times as you want and not have it lose its elasticity, not have it fall apart on you. That'd be nice. What? But we can't come up with it. We're stuck with rubber. Well, what's the problem? The problem is, go to Sam's, go down the rubber tile aisle. Can you smell it?
Yes.
Yeah. That's as long as that rubber's around, it's going to be emitting all this organic gases. Well, if you're using a gas chromatography, a GC, and its sole purpose is to detect organic gases, you've got a huge problem here. Your background is tremendous just because of that septum. And the septum is hot. It's got it in this inlet. You have some big issues here. So the whole time, you've got a septum purge outlet. So there's going to be a number of ways where gases leave, where the mobile phase, the hydrogen gas, leaves this inlet. Here's one of them right here. This is way number 1, right? The gas enters, goes down. Look where it goes. It blows right by this thing. And it just kind of removes the air in here. Tries to get rid of that stuff. You still have a huge background with GC due to that rubber septum. And they heat the crud out of those things. They treat them. They do everything. They can't stop it from kicking out those organic gases because it's rubber. So the septum purge outlet, constantly blowing that. That's one way to leave the inlet. The other way to leave the inlet is, well, right out of the column, right? That'd be the second way to leave the inlet. Just have the gases just, right? It volatilized and it left the column, goes through the column. That's how it leaves the inlet. The third way is what you guys have been playing around with on the GC lab, the first one. You split, right? So when you turn this on in the computer, right? It's going to take a lot of that, it's going to add a lot of mobile phase and have a lot of it just leave the split outlet. And if you follow all these little lines on the back, there's this little white line that goes all the way around and back into the fume hood in the back. So same for the septum purge. That's where all those lines are going. The purpose of the split outlet is to do what? Why do we mess with it, Andy?
Well, the split outlet
Yeah, why do you mess with this?
is it's hooked up to the column.
Well, and you know, right on top of it, yeah. So it's going to,
What's going in is
the D word, it's going to, well, you don't want your stuff to decompose, otherwise you can get all these peaks. And your stuff, you're not going to know what it is. So that's decomposition is why GC can only handle what % of the compounds in the world? 20%. Rough. It's a rough guess, but around 20.
What are the arrows for?
That's just showing the flow rate, where the direction of the mobile phase.
So the higher
So the purpose of this, if you can run things in split mode or split less mode. Split mode is when you're using the split outlet. You're going to run it 100 to 1, 10 to 1, 25 to 1. All you're doing is just diluting your sample. So 25 parts per 1. Only 1 part out of 25 actually goes down the column. The rest going out of the instrument. Dilute it 100 to 1. Well, only 1 part goes down, enters the column. The rest goes out of the instrument. And it's a gas, so 100 to 1, it sounds really exact. But if you're sampling gases, it's not exact. So that's why you're supposed to use what standards all the time? Internal standards. When you want to quantitate with the GC, you're supposed to use internal standards. Okay. But it's just an extra step, so a lot of times it introduces more air than it helps for beginners. But so we mentioned the 3 ways you can leave the inlet. Okay. If you're running in split less mode, how many ways are there to leave the inlet? Just 2, right? Because you're running in split less mode. What would be your guess here, Brandy? Over what % of all problems occur in the inlet? It's 90. This is where all the gunk is, right? You inject stuff. This is where it's all going to end up. The stuff that doesn't volatilize, it decomposes. You get, our peaks aren't pretty anymore. Look at all, there's multiple peaks. You may not have even injected correctly, right? There could be a lot of issues in there. So that's pretty much where all the problems are. There's let's see. Did you see this is the one we didn't mention, the glass liner. So those things I underline is what I think you should have in your little flow diagram. The glass liner is, here it is, and some rubber septa are in there. So if Andy does inject Coca-Cola into the GC, all the sugar is going to end up in the glass liner, right? Because it's just caramelizes, right? Sugar's not going to volatilize.
So you have to change these out pretty often.
Yeah, you just pop them out. What is sample overload? What would that be?
Too much sample.
Yeah, too much sample to all vaporize at once and enter the column, enter the capillary column. How can sample overload be avoided from the start? That's a hard question. You could just do trial and error. Or use this computer program. Okay. For example, in our what was that? Looking for ibuprofen in sewage treatment water before and after the sewage treatment plant. How much can you inject? Well, it'd be really nice if you could just calculate it. So here's a flow calculator program that's supposed to help you do that. And what you do is you pick your liner, right? And these are all product numbers. We know which one we have. And I think that's it. And our solvent is water. You look at your method and see what the inlet temperature is. Usually it's like 250. It's a very common temperature to have it at, 250. The inlet pressure, right around 14.6. That's a common pressure. So how much can you inject and not have sample overload? It looks like 1 microliter is too much or too little.
Too little. Because we inject.
Can we inject even?
microliters.
Can we inject even more? And I'm just talking about what this computer instrument tells you. There's a little red light on overload, so it probably means too much, right? So we need to, if we inject more, now it's just going to stay red, right? So you have to inject less. Now, and it's getting questionable now. Okay, so around 477 microliters is the maximum you can inject. And water sounded like such a wonderful solvent to use. It's just that you can inject very small volumes because it really expands. If you pick something else, pick anything else, you can inject a lot. Look at that. So water just really expands. So it's a wonderful thing to use with the FID, but you can't inject a whole lot. Okay, so have a good weekend.